So today we're going to look at the frequency analysis tools for CME version 8.1 released. The frequency analysis tools contain some new features and some new firmware. So take a look at the note. This is part of the CME user guide too, but there's a separate note for frequency analysis. And of course, safety is very important. So open loop testing is dangerous. Be sure to set some limits, velocity limits, position limits. And the available modes of operation include the new modes. We've always had current closed loop, velocity closed loop. But we've added some high frequency, velocity open loop, low frequency, velocity open loop, and the velocity plant. High frequency, low frequency, position plant, low frequency, high frequency. And these have been tested and confirmed or validated with the professor of control theory. So they are very accurate and very good. So that's maybe an improvement over previous versions of the frequency analysis tool. But there are three general types of frequency analysis modes. There's the closed loop, which is obviously not open loop, so not so dangerous. And then there's the plant. And these can be described with the following block diagrams. Closed loop refers to controller and plant with feedback. Open loop refers to controller and plant without feedback. And plant refers to the system without feedback and without the controller. The controller always refers to the outermost control loop controlling motion. Example, the position controller in position mode. The plant always includes the motor and load and indicates the closed inner loops. Example, when controlling velocity, the plant is comprised of the motor and the load and the closed loop current. Okay, as if that was not clear enough, we have pictures. So the plant and the controller and the feedback going to the summing junction. So current function generates a sine wave. And this is looking at, I guess, the current loop with the inductance. But you got your output over input for analysis of the transfer function. You get your open loop, so there's no feedback, and it controls the controller and the load, output over input. And then the plant, the command goes to the plant, and hopefully that is very clear. So high frequency, HF, low frequency, LF, and then S is for servo. So you're in a servo loop. Just going to do a quick peek at the setup here. And we have today a Mitsubishi motor connected to a Copley nano drive. And we could see little tiny Mitsubishi HK motor with absolute feedback, nano plus drive. That's the easy board on top of the nano module. And there's the easy board mounted into the development kit. For the current loop tuning, I'll block the shaft of the motor. But let's take a quick peek at the wiring because that comes up. So I just busted open this connector for the feedback, and there's HK wiring. So you got your power on red and white, okay? And you got your data on green and data not on blue. And then there's the older HG wiring. This one shows a battery, and you get your shield, and you got your data on yellow and your data not on brown, your battery on red, the L ground on white and green. I guess that's for the battery, and then the black, of course, is the power. Oh, black for plus 5 volts. What do you know? So this is just a wiring to a XLNet or a Zenus drive. This small motor is good for the nano. We'll take a quick peek with CME and just basic configuration. If you're approved for semiconductor or electronics, you can get approval through Mitsubishi to use their feedback type. We'll have to unlock that with passwords from CME. But you get your HG and your HK type. I guess this is an HG motor, 18-bit, absolute single turn. Oh, it's got CRC fault on power up, so I'm just ignoring that. So probably just a cabling thing. Position mode, got some data for the motor, poles, inductance, resistance, back EMF constants, all the good stuff. I had calculated initial tuning parameters and did some of my own tuning. So you can see the current loop's been tuned, small signal. That's gives me about 500 hertz current loop bandwidth, but it tends to give me bandwidth further out. We'll look at that at the frequency analysis. I actually can go like 8,000 RPM with this motor, and there's no problem getting current out of the drive. So that's curious, and we'll use the frequency analysis to take a look at that. I did tune up the velocity loop, so we can see the command and actual, and I put a pole at 300 hertz just so we can see it in the frequency analysis. So I single pole moved out to 300 hertz, and I cranked up the gain. This ripple is just cog. It's a very small motor with high force, so maybe it's got some kind of iron core. And then, of course, for position loop, to what is the counts per rev? So on the feedback, 262144. So I'm just going to do a single turn, 262144, 2 to the 18. I lowered the VFF and I set my integral not too high. And there's no load, so my PP is at 1,000. So we'll see a move and settle. That should look pretty good there. So maybe a little bit more integration would be good. Give it 75 and we'll move it again. I wonder with the cog if we're just sort of in this cog range at the final last few counts. Yeah, so I'll split the difference. We'll say 60 for integral. Don't put too fine a shine on it. This cog at the last few counts. So it does integrate in, looks pretty good. But we'll take a look at this on the frequency analysis tools. So without further ado, frequency analysis. The first one I'll look at is the current. This is a small signal amplitude. I locked the shaft. There, I locked the shaft. So we got up to about 50 hertz before I locked the shaft. So it should go out flat and then start rolling off. Maybe around 500 hertz, because that was the bandwidth I tested. But I noticed that at higher sine waves, I could go out further. So I'm going to take this out to the default 3 kilohertz. We're going to do 50 samples. That's fine for current loop. This is just showing us how to use the tool. It's probably of not much value. Yeah, you can see what happened when I locked the shaft. So when the motor's moving around, it's kind of hard to measure stuff. But when you lock the shaft, 0 decibels, goes out flat, rolls off. So current closed loop, so 0 dB. And I get a 3 decibel, 3 dB point right about here. 1, 2, 3, 4, 500 hertz. But look what happens around 600 hertz. It is a 0 here or something, and it goes out further before it rolls off. So I can get some pretty high bandwidth. I can get current out of this when I rotate the current vector, which is nice. There's a little half power point coming on sooner, but I can still go wicked fast with this motor. There's a velocity closed loop, velocity open loop. I'm going to look at 2 more plots here if I have time. So I'll do the velocity plant low frequency, velocity plant high frequency. We'll save it as a comma separated value, and we'll use that for further analysis. But so low frequency, I don't know, you could start at 1 hertz if you want and go to 500. I'm going to do 50 samples here. Actually, I'm just going to do 20 samples. You should do 200 to get like lots of data, but do this again for the high frequency and save the 2 files in a CSV format for analysis in MATLAB. And so this is gathering the frequency. I'm going to remove had the clamp on, so break free at around 2 hertz. I let the motor turn. That should be interesting. So ignore the low frequency on the plot because I had the shaft stalled. It wasn't moving very much. But now it's rocking and rolling a little bit. Take a look with the camera. Can't see the motor shaft very well, but you can hear or feel a vibration now, but it was shaking back and forth a little bit. So watch out for, hitting the hard stops or any limits, current limits, and whatnot. So yeah, as you can see, with the motor shaft locked or stalled, you didn't gather very good decibel data. But so your open loop or your velocity plant shows a very high decibel, 145 dB, and it goes out and rolls off. But there's something happening here around 10 hertz, and then you get your normal, roll off. And then, of course, you would want to gather this again at the high frequency, and we'll pick up, we'll do like 300 hertz, and yeah, why not? Again, you should do 200 samples, gather larger data. So you just, for the low frequency, gathers good information for the lower frequencies, and the high frequency, of course, gathers better for the high frequency. Yeah, so there must be a pole around 300 hertz. We know there's one in the velocity loop. I got some integral in there, so there's an integral break frequency that should carry my velocity out further. So that may be why I'm not rolling off. Well, it could be 20 dB per decade, so that does appear to be so. But this is the plant, velocity plant. Okay, so we can see the roll off and the phase shifting, and then this is just a wrap. It doesn't really jump up this way; it just continues down further on. It's just a way to plot with a wrap. And so you just save these, save current plot, and you can give it a name like velocity plant, high frequency, velocity plant, low frequency. And that, in conjunction with the CCX file, is probably all the data you need for the analysis. But the data is good to gather, and the analysis can be done in MATLAB if you want to do your own custom biquad filters or something. Okay, thanks for watching the latest frequency analysis tools.